friends, welcome to VK Lectures. In this lecture we will be discussing about the classical system. We will be also looking into the classical averages and the equipartition theorem. Now let us discuss about the classical system. So far we were dealing with discrete system where particle is having discrete energy states. So here we are dealing with now classical system. Now what is the idea for classical system? The basic idea is it has continuous energy levels. Continuous energy levels. Okay, now for the discrete energy levels, we had the partition function z given by sum over es e to the power minus beta es, where es represent the energy of each state. Now this is a dimensionless quantity. Similar to our wave function, this partition function z is partition function. Now when the energy levels, now we have discrete energy levels, and when it moves to continuous energy levels, that means you do not have any gap between them, so it's completely what you say, it's do not have any space, it is all continuous energy levels. So when the system moves from discrete energy levels to continuous energy levels, the partition function, in the partition function the summation get replaced by the integral. So instead of summation we have integration, and this is with respect to the dq dp or dp dq, where dq represent the position, this is dp represent the momentum. So the energy h, or the Hamiltonian h, which is a function of q and p, so q p. So earlier we had the z which is given by sum over for discrete energy levels e to the power minus beta es, while for z classical system we had sum over integral over the limits we can do it later, e to the power minus beta es. Now this es will be function of p and q, or qp, the position and momentum, thus the integration will be dp dq. Okay, or we can write about ith particle. So this is how the z classical is written. Okay, yeah. Now what is this dpi into dqi? dpi into dqi, this represent the volume of the phase space, volume of phase space. In 3 dimension we can write dx dy into dx dpx, not dy, dpx, dx into dpx. This corresponds to 1 dimension. Then dy dpy, the second dimension. Then dz dpz. So this is a volume in 3 dimension. Now when you integrate this, this will have some dimension. To make this dimensionless quantity, we will divide, since it is 3 dimension, we will divide it by 1 by h cube integral e to the power minus beta es into dpi dqi. Okay. Now we have seen the partition function for a classical system in 3 dimension. 3 dimension is given by 1 by h cube integral e to the power minus beta e dpi dqi. Then for a 1 dimension classical system, 1 dimension can be written as 1 by h integral e to the power minus beta e dp dq. Okay. Now again on simplified, making it more simplified, the z, the classical system, can be written as 2 pi em kbt by h square whole to the power 3 by 2 into integral minus infinity to plus infinity e to the power minus beta into sum of u of qi into dqi. Now for this is for 3 dimension. Again the z classical for 1 dimension simplified formula is 2 pi em kbt divided by h square whole to the power 1 by 2 integral from minus infinity to plus infinity e to the power minus beta into u of, u means the energy, u of q into dq. So for a classical system, one of the application is ideal gas. Ideal gas, this is for classical systems. One of the best example that we can take is ideal gas. Now since for the ideal gas there is no interaction between the gas molecules, therefore sum of I, the energy, interaction energy u of or ui of qi is equal to 0. Now what kind of system is the ideal gas? Ideal gas is an example of a 3-dimensional system. So energy, which is given by E, is equal to sum over I equal to 1 to 3, pi square divided by 2m plus sum over u of qi or ui of qi. Now we need the classical system partition function, which is equal to 2 pi m kbt divided by h square whole to the power 3 by 2 integral minus infinity to plus infinity e to the power minus beta into sum of ui of qi into dq. Now we already have seen this part is equal to 0, which means this is dqi. Now this becomes 2 pi m kbt by h squared whole to the power 3 by 2 into integral dqi is from dx dy dz, which is nothing but the volume. Now this partition function z for ideal gas is v times 2 pi m kbt by h square whole to the power 3 by 2. So this is the partition function for ideal gas. Now for n number of particles, so here we are dealing with single particle, so because we had only I equal to 1 to 3, single particle 3 dimension. Now for n particle system, if there are n particles, then v power n, okay, let us write z n particle system. N particle system, v power n 2 pi m kbt by h square whole to the power 3 by 2. No other changes will, sorry, here 3n by 2, 3n by 2, no other changes. In the case of ideal gas, there is a concept called thermal wavelength. Thermal wavelength. Now we have seen for n particle system, n particle ideal gas system, the partition function z is given by v to the power n 2 pi m kbt by h square whole to the power 3n by 2. Okay, now what is the thermal wavelength? Thermal wavelength is given by lambda t is equal to h divided by under root 2 pi m kbt. So this is the thermal wavelength. Now whatever is there. Now what we can do is to write the z, the partition function, in terms of thermal wavelength. So z can be written as v to the power n into 1 by lambda t squared, because h square and 2 pi m kbt, whole to the power, so here there's no change, 3n by 2. Now what we can do is, again this can be arranged, v to the power n divided by 1 by lambda t whole to the power, instead of 3n by 2 only 3n remains. So this is the z for ideal gas. Another example of classical system is so classical system, another example is the classical oscillator, linear harmonic oscillator, the same thing. Okay, classical oscillator, we know the energy E is equal to px square. This is one dimension. Classical oscillator, one dimension. There are two dimensional and three dimensional oscillators, but here we are considering only one dimensional classical oscillator. Px square by 2m plus half m omega square x square, where m is the mass of the object, omega is the frequency, px you know is a momentum, x is the position. So for one dimension, z one dimension, the partition function is given by 2 pi m kbt by h square whole to the power 1 by 2 into integral e to the power minus beta into u of q dq. So what is u of q? The potential energy is equal to half m omega square x square. Okay, so replacing it, z, this one can be written as 2 pi m kbt by h square whole to the power 1 by 2 integral e to the power minus beta into u is m omega square x square by 2 dq, only along one direction x, and is from minus infinity to plus infinity. Now the same thing, 2 pi m kbt by h square whole to the power 1 by 2, the integral of e to the power minus beta. So integral from minus infinity to plus infinity, e to the power minus beta x square. This is, you can write alpha x square. Alpha x square, this is the Gaussian function integral dx is equal to 2 pi divided by the coefficient of x square, sorry it's not 2 pi, it's pi divided by coefficient of x square whole to the power 1 by 2. So pi divided by coefficient of x square is beta m omega square by 2, so that b2 will become 2 pi whole to the power 1 by 2. So this is z classical for one dimensional classical oscillator. So this becomes 2 pi, here we have 2 pi, this is also 2 pi, so 2 pi into this beta is here 1 by beta, so beta is nothing but 1 by kbt, so beta goes to the other side, it becomes kbt, so 2 pi kbt, and m gets cancelled on different sides. Then again we have h square becomes h, and what is remaining is omega, root of omega square is omega, so that is equal to z classical is equal to this kbt can be written as again 1 by beta, so 2 pi by h, this becomes h cross, so this is 1 divided by beta h cross omega, where h cross is equal to h divided by 2 pi. So this is Z classical system for one dimensional oscillator. So for a classical system we need classical averages. So classical system needs classical averages. So how to calculate classical average value? Okay, now for the partition function z in a discrete system, we have sum over es e to the power minus beta es. Now this average e or u is given by sum over es e to the power minus beta es divided by z that is the partition function, that is e to the power minus beta es. Now if we need to find the expectation of e squared, that will be equal to sum over es square e to the power minus beta es divided by sum over es e to the power minus beta es. Now and for any discrete system, any discrete function f, the average of this function f is given by sum over es f e to the power minus beta es divided by sum over es e to the power minus beta es. Okay, now if f the function is continuous, for a continuous function, or it's for a continuous system, not the function, for a continuous system with the energy which is being continuous, so we can write the classical form, that is the average value of the classical. You can replace the summation with the integral f e to the power minus beta e dpi into dqi divided by integral e to the power minus beta e dpi dqi. This is an example for finding the classical average of the function f. Equipartition theorem. What does this theorem says? Now for any particles the energy is given by sum of the kinetic energy plus the potential energy, that is px square by 2m plus half m omega square h square. Just for example, we can consider the linear harmonic oscillator. Then the average value of E is equal to px square by 2m plus half m omega square px square. The first one gives the average value, that this one gives accounts becomes half kbt, and the second term also becomes half kbt. Now this implies that each quadratic term in the energy function in energy contributes to half kbt to the mean energy, Now here we have half kbt plus half kbt, so kbt. So this is linear harmonic oscillator one dimension. Okay, now if it is ideal gas, it is 3 dimension. There is no potential energy, there is only kinetic energy. So kinetic energy in all 3 different forms. So total energy is equal to half m vx square plus half m vy square plus half m vz square, or you can write px square by 2m plus py square divided by 2m plus pz square divided by 2m. So this is the energy. So what will be the average energy? Average energy will be equal to 1, 2, 3. So 3 by 2 kbt. So this is the average energy for ideal gas.